Hello and welcome to a talk on Subvl, the extension to OpenPOWER instruction set, which provides a rather unusual type of vectorization. With many thanks to FOSDEM organizers and to the OpenPOWER Foundation for this opportunity. This talk is I'm going to do this in a bit of an unusual way. I'm actually going to do it directly from a page that's on the website, using IkiWiki. Way, oh, good fun. So please bear in mind, Subvl is in development. It's in draft status. We will need to present it to the OpenPOWER Foundation, the ISO working group, for review. And until they've had a look at it and gone over it, it is not an official part of the OpenPOWER instruction set. That's very important to understand. So this will be what we'll go over. You can actually follow along if you want on this page online, because it will be exactly the same contents thing. So you can actually see the full page if you want in your own web browser. This is an open project, so there's a discussion link and there's a bug report if you want to provide comments, ask questions and anything like that. It's absolutely fine. The purpose of this particular page is to give you an understanding of what the vectorization system is. The actual format, SVP64, is the instruction format of how the bits are put together, which doesn't you need to understand. You need to understand what it is that is going on behind the scenes, and that's what this overview is about. And then there's the main page, which links to several things, including the augmented instructions, the some of the transcendentals that we're going to be adding for 3D GPUs, etc., etc. So the basics here are, what we're going to do is go over the fundamental, the core of what the vectorization system is, and it's just 2 lines, literally in pseudocode. It's literally 2 lines of code. All right. Then what we're going to do is introduce more and more concepts on top of that, which will expand it up to the full capabilities that you would normally expect of a modern vector system. Now, before we get there, it's important to understand what actually the difference between SIMD and Cray vectors. And there's an extremely good article written by the RISC-V founders called SIMD Known to be Harmful, which is on SIGArch. And what they did was they revived the old Cray-style vector system. So let's take this usual loop of DAXPY is a simple for loop. Y equals each parallel item in the vector is basically y equals mx plus c. So you add the things on. Now they've assessed, in the table below you can see that they've assessed the different instruction sets, and the number of instructions is it's ridiculous. Look at that for static instructions, 22 versus 13 for MIPS, 22 for MIPS and 13 for the for RV32 vector thing. Bookkeeping instructions 15, RISC vector RV32 3. All right, this is highly significant. When you do things like string copy, we'll come across an example of this later. The Power 9 string copy routine is a whopping 240 hand-coded assembly instructions. So where the people who wrote this article are being polite and underestimating things, in reality it is horrific. the overhead. But more than that, the thing that took me a while to notice here is look at the dynamic instruction count here. The actual number of his instructions, because of the effectiveness of the SIMD instructions, is very, very low. And you have to go round the loop basically a huge number of times. So in the result per main loop, 2. So that means that if you're doing 1,000 values, if n in your loop here is 1,000, you have to go around this loop 500 times. Whereas for RV32, if the lane width is 64, and it can be any arbitrary length that you want, as in your hardware, then you're looking at 1,000 divided by 64. So the number of times that go around the loop is much, much lower. And the effect that has is that your instruction decoder sits idle. The instruction size is the program size is less, the actual number of instructions executed is less, your usage of your level 1 instruction cache is less, and consequently you're reducing power purely from doing more with the back end of your architecture. And what's even more fascinating is that you do not need to change the program depending on what the implementer provides in hardware. The implementer can do a vector lane of 1, or they can do, as they used to do in the old Cray systems, vector lanes of 10,000 units, where the register file had to be external static SRAM. It's amazing stuff, the Cray things. Anyway, so moving on. Here's the actual assembly code, and the core instruction here is this set VL, right? Where there's the VL, the vector length, is a controller of how many elements will actually get executed in any given loop. So you have in your hardware backend, you have say 10 lanes. That is your maximum vector length. And set VL, set the vector length. If that gets set to 3, then only 3 of those lanes will actually be used to compute answers in your vector. All right. So the way that it works is you request 10,000. You actually only get 8 because your hardware only has 8 lanes. That gets put into one of the registers so that you can subtract that later on. Or subtract, there you go, your count A0. So the relationship here is A0 contains your 10,000, but after you've done the vector add, you subtract the value T0, which contains the vector length. So if there were 8 done, you would go down, thing. And finally, on the last loop, if it was a non-power of 2 value of n, initial value of n, you would end up with, say, 3 or 2 or 1 items executed. And notice here, there is no setup SIMD stuff. There is no cleanup, tear down nonsense at all. This exact same program works whether there is 1 lane in hardware or 10,000 lanes. Okay, it's exactly the same code. That is really significant. It's why we decided to base Simple V on this, on a Simple V on Cray vectors. So, the other reason for using this vector system is because your typical SIMD proliferation, it's mental. Alright, the multiplications on the instruction set, you've got your operation, add, multiply, subtract, whatever it is. That's one dimension, of which typically you'd have 20 to 30 operations. Floating points you'd have maybe 30 or 40. If you do the transcendentals for a GPU, including sine, cosine, log, and etc., you'd have 40. All right. Then you have multiplied by the bit width. Okay, so your 40 instructions now gets multiplied by each of those dimensions. So you have an add 8, an add 16, an add 32, an add 64, and an add 128. Right. Then you have to have conversion between those different bit widths, which involves Pascal's triangle of opcodes. Then you have signed and unsigned. Okay. All right. So you have signed operations, which doubles your number of instructions again. To be, I'm exaggerating, but this is often the case. DSPs, particularly the Andy Star audio DSP, they put the left and the right channel audio data into different parts of a 32-bit register or a 16-bit register, and consequently, in order to interact with them, you have to have a high add, a high add, a high low add, a low add, and a low high add, and then a high multiply, and then a high low multiply, a low high multiply, and a high multiply. It gets mental. All right, and then if you for audio and other things for for video things, you want what's something called saturation, where at the maximum range of the operation you end up with what's called clamping. So it doesn't roll over modulo. If you've got a 16-bit operation and it goes over 64K, the value is clamped to 65536. It doesn't wrap and roll and corrupt the data, because that results in audio corruption. It's just basically random noise. So again, you need to add yet another dimension onto your instructions, and you can see very easily why you get these monster mental instructions. Several thousand instructions, which massively complicates your instruction decode and your issue engine. It's just it's nonsense. And every single addition, Intel's up to 512-bit. AVX 512 is what's next? 1024? They're going to have to double the number of instructions in the entire instruction set. They're already up to 128-bit instructions, variable length. Mental. So what we do instead is in Subvl we've actually abstracted these out. It's a prefix applied to a scalar instruction. All right. The only thing is though that even RISC-V suffers from this. Suffers from this overkill. The RV64GC is only 80 instructions, but the RVV is a whopping 188 additional instructions. So it's not just SIMD that suffers from this opcode proliferation. So here's the basics of SV. The program counter gains a counter, all right? So it pauses the program counter and runs a sub-program counter loop from 0 to the vector length, that Subvl instruction we saw in the other code. Now, it's important to note the program order of these sub-PC instructions must be preserved just as expected of instructions ordered by the PC, and that becomes relevant for if you do an out-of-order execution engine, all right? Some of those registers may be tagged as vectors, and during that sub-program counter loop, those vector tagged registers are incremented by 1 with each iteration, executing the same instruction but with different incremented registers. And once that loop is completed, only then will the program counter be allowed to move on to the next instruction. I appreciate I'm just reading out the slides. You're not supposed to do this, but hey. Okay. So that gives you the basic concept, right? And it means that the hardware implementations will be, it is literally a for loop, okay, for simulations, etc., etc. All right, and here. When I said I wasn't kidding, it was 2 lines of code. This is basically what the loop does. We use the OpenPOWER ISA v3.0b pseudocode here. For I equals 0 to VL minus 1, GPR RT plus I equals GRP RA plus I plus GPR RB plus I. And so in this way, when you get an SV context augmented add with VL equals 3, and it's add R0, R10, R20, then what will actually get put into the instruction queue is add R0, R10, R20, add R1, R11, R21, add R2, R12, R23, 22. All right, so it's genuinely that simple. All right, and we do not add vector instructions. This is critically important to understand about Simple V. We do not add vector instructions. The scalar instructions become vectorized, in effect, through the addition of an external context. Okay? And what this means is, to give some examples, these actually come from the Simply Considered Helpful article. x86 back in the 1970s was 80 instructions. Before AVX 512 was added, it was expanded to 1,300. Again, as I mentioned earlier, RISC-V is 180 instructions. That's more than RV64G, which is 80 and 27 for the compressed thing. I mean, that's just it's nuts. OpenPOWER v3.0b, it's around 150 instructions in the integer scalar ISA. There's about 80 more from the floating point. I'm including some of the RC equals 1 for the overflow versions there as well. But VSX adds somewhere around 600. I mean, and it's SIMD, so the OpenPOWER can't expand beyond these 16-byte instructions. It doesn't have predication. So Simple V adds predication and saturation and many other features from using these contexts. Okay. They also have to add all these things: AVX 512, SVA2, VSX, and RISC-V. They all have to have different types of register files. AVX even has this mini mask register file and associated instruction set with it, because they couldn't use the main core thing, because the distance, as explained in Tim Torside's excellent video, it's very, very funny. The distance between the main x86 scalar processor and the vector one was so far that the latency that would have been introduced if they'd used the scalar x86 registers would have been mental. I mean, you've already got huge latency when you're executing AVX 512 instructions anyway, but that would have been made even worse. And so they actually had to add a mini mask register file with instructions in them, just to compensate for the fact that the distance on chip was too large. Okay. So being fair to both VSX and RISC-V RVV, there are some things that are not provided. We don't do 128-bit arithmetic or above. We don't do register files above 128 entries. The vector lengths in Simple V are restricted to 64 entries only. And we're having a bit of fun and games adding unit stride load store, but we've actually just managed to work that out. We're restricted to 32-bit instruction lengths, where the context extends those to 64-bit. RISC-V vectors are 32-bit, as are VSX. So we have to do quite a lot more work in order to gain the benefits of the power saving from the instruction cache, etc., etc. But this is just, it stems from the adaptation process of starting from a scalar instruction set. So what we're going to go over next is the addition of the following features: vector scalar, scalar vector, scalar scalar on all the register files, integer, floating point, and the condition registers. We're going to show how we create, without actually having any vector operations, how we add vector operations: vsplat, insert, compress, and all expand, etc., etc. We're going to add, show how predication masks are added, which are essential in 3D for parallel if-then-else constructs. We're also going to show how you do 816 32-bit initial operations and floating point 16 and BF16, despite the fact that the instructions are designed as 64-bit. How those get compacted into registers, which something you'd normally only do for SIMD. We're also going to show the fail-on first concept briefly, and a new concept of data-dependent fail-on first, and yet another new thing, which is condition register-based post-result predication. And another new concept called twin predication, where you predicate both the source and the destination. And we also have to add vec 2, 3, and 4 subvectors and swizzling, which is standard fare for 3D. And swizzle operations are something mental, like 10% of operations in 3D shader applications. So you really need them. But all of this is done without modifying the OpenPOWER v3.0 instruction set, except to add the this wrapping context. So let's move swiftly on. This is how we'd add the definition system of scalar and vector. So every single instruction, every single register, every single operand of each instruction has a tag indicating whether it has or has not been vectorized. So RT has an is vector, yes or no. RA has a is vector, yes or no, and RB has a vector, yes or no. And that simple loop, which previously was just GPR RT plus I, it becomes GPR RA plus I plus GPR RB plus I. We detect we have three separate indices, one for RT, one for RA, and one for RB, and we increment them independently depending on whether they're vectorized or not. And in the case of the add operation, but not for cache inhibited load, I'll come on to that later if we've got time. The loop is exited if the destination was a scalar, but only after the first result is created. So I could have written this out as 8 separate cases of pseudocode, one for vector, 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 scalar, vector, scalar, scalar, vector, blah, blah, blah. You get the idea. There's 8 cases there because there's 3 registers. That when you combine those in pseudocode form optimally, results in this. Okay. Now, there is no separate scalar add instruction and separate vector instruction. And there is no separate vector register file. It is literally the same scalar instruction set and the same scalar register file. Okay, and consequently, we can view Subvl as not being vectorization at all, but as a hardware compression scheme, because you are literally taking the add R0 blah blah blah, add R1 blah blah blah, add R2 blah blah blah, blah blah blah. Sorry, I have a daughter. We really appreciate that stupid film with Adam Sandler in it. It's a hardware compression scheme. So those 3 instructions, because the registers were sequential in order, could be substituted with one instruction with this loop. Okay. It's a hardware loop, and consequently you need the program order is important to preserve it, but it's where this decision comes from. It's that thing. All right. Now, we also need to extend the registers because GPUs don't really work unless you have a minimum of 128 registers. All right, and the reason is because you're dealing with 4 things at once. You're dealing with vectors, typically your quads, X, Y, Z, and W, or A, R, G, and B. And you need to operate on those, all 4 of those things at once. And so consequently, quadrupling the size of the register file is a critical minimum, without which, if you didn't do that, you would end up with spill back through the level 1 cache and so often into the level 2 cache, and there is a huge power consumption penalty for doing so, which was illustrated very kindly by Jeff Bush's NIUSI research. So what we do is we have you can see the link here in SV664, which you can have a look at it. We have some tag bits, so we don't just have a tag bit for isVector here. That's one of those bits, but what we do is there are 2 additional bits which are tacked on to the 5-bit RA, RB, RT to extend the instruction, the range of the registers from 0 to 31 to 0 to 127. Okay, and in future versions we can shift this along by another. This here we can shift that calculation along by 1 to give 256 registers, and by 2 to give up to 512. Okay. Condition registers are slightly different. I won't go into them now, I think, but the complication is the fact that you've got bit addressing. The condition registers are there's actually 8 of them. We're going to have to do 128, and one of those produced per vector result. So there'll be a corresponding. If you'll start from CL0 for integer operations, and it will go up. For every vector result, you will get a vector CR. And that's completely different from how VSX works, where they actually post-analyze the 16 bytes of the VSX register, and you get one condition register which tells you about those results. We're literally doing one condition register per vector element, which is a lot more flexibility and a lot more powerful. So next step, add predication. And behind the scenes, you'll see in the other pseudocode look around, you have the ability to get the predicate value, which can either be a scalar integer condition register, scalar integer, or we can use the condition registers starting from a thing, and we pick one of the fields. So you pick the EQ field across the vector of condition registers, a vector of condition registers. You pick the less than LT field of the vector of condition registers, or the GT or the SO field. Now, the loop here previously, this was just, there's no predication here, all right? And all that predication does is it tests each individual bit, and if that bit in the predicate is not set, then it just skips that element. Okay, so the key modification is to skip the creation and storage of the result if the predicate bit must be clear, but not the progression through the registers. And consequently, this is where it becomes much more powerful thing, because you've got 8 possible combinations here of the consequences of this predication skipping, right? And what that turns out to be is that you end up, if you look at it closely, I'm running out of time, so I've got to move quickly on. You end up with all of these types of operations, vinsert, okay, because here you set the destination for vinsert. You set the destination as a vector, and you set one of the bits of the predicate, and that will skip. Oh, one of the bit is set. I'm doing an insert now. Yeah, but it's an insert of the computed value. So there's even more flexibility and power of this system. That normally vinsert is restricted to a move operation, whereas here what we've got the vinsert abstracted concept applied to all operations, all arithmetic operations, and load and store. Okay, vsplat, what you would do there is you would set the source as scalar, both of them, R, A and B. You would set the destination as vector, and then you would simply run this for loop, and your predicate, you would set that to all once, and that would broadcast splat this scalar computed result across the entirety of the vector destination, multiple registers. And if you didn't want any of those particular ones to be set, you just exclude that particular bit. Now, in combination with the condition registers, you can start to see where the condition registers created a vector of condition registers that can then be used as the source of the predication. You start to see why it's become so powerful, and also why we decided to do vector condition registers. Then we've also got a vselect. You can set that up thing, but all of this capability was without adding one single actual vector instruction, not one, let alone 180 or 600 or 1300. So sometimes in predication you want zeroing. There are various reasons for that. So what we do is we modified again. We're going through modifying our pseudocode incremental step-by-step thing. So you simply set a zeroing mode where if the predicate bit failed, then rather than skip it, you zero out the destination element. And so many vector systems either have zeroing or non-zeroing, but they don't have both. But down to the way that if you don't have zeroing, then typically your architecture would have to have a read, modify, write cycle and a thing. But if you instead use out-of-order execution, you can actually get away with that. And also you can do byte level masking on the register file. And you can do both. Element width overrides is a particularly important part of the system. We have an override on the instruction which changes the bit width of the operations. This is where it gets particularly interesting. Now, read hair raising. So in C, this will be your typical register file definition. You'd have a type def of a 64-bit to reg_t, and you would then have 32 of those in an array. Okay, so hold on to your hats. We replace that with the following structure: a type def which is a union covering the original bytes with an array array pointer of 8-bit, an array pointer of 16, array of 32, and an array of 64. Okay? And consequently, when you start indexing B here, B here will go from 0 to 7, will be in the first actual bytes entry here. But after you go to, when you go to 8 to 15, it will roll over to the second 64-bit register. Okay, and so here's let me think. to illustrate that, here you can see we've got bytes 0 to 7, and you're starting off in R0, which would be indexed in register file bracket 0. You start off, B0 goes here, the thing, all the way up to byte 7, but then it will roll over into R1. Okay, and likewise, if you have 16-bit values, your short 0, byte 0 and byte 1 go in R0, byte 0 and byte 1. The short brackets 1, byte 0 and byte 1 go into byte 2 and 3 of R0. Short 2 goes into byte 4 and 5, and short 3 goes into byte 6 and 7. And then you roll over to register 1 for short 4 thing. And the critical thing to note is that if your vector length was 7, bytes 6 and 7 remain unmodified. And this is a very, very important feature of Simple V. Okay, you do not destroy the high bytes of each of the 64-bit registers. Okay, and in technical terms, what has to be done at the hardware level to support this is either a read, modify, write cycle, or you can do byte level write enable lines on each of these things, and that interacts very well with the predication masks. Excuse me. So when you want to get your element polymorphic register, you simply access it via the bit width, returning reg.b, reg.s, reg.i, or reg.l. Excuse me. Setting that up and return the thing via the offset on this. And to set it, you do a similar thing. So you're accessing the array in the type def union and using that as a means of explaining that we end up overwriting the actual bytes underneath. And then very, very simply, that simple loop, that two-line loop that we had earlier, you use these get the polymorphic register source 1, get the polymorphic LRB, and then you do the set there. Okay, so that's really it. And in the simulator that I did, it was literally I did exactly this. I wrote a get polymorph reg function and a set polymorph reg function and used them, and that was pretty much it as far as modifying the scalar simulator to create it turn it into a vector one. All right. Really running out of time. I won't go into that. Now, yes, as a minor complication, if you have element with overrides on both the source and destination, and this is relevant for floating point. So what we have to do is you have to do the operation at the maximum possible width thing. All right. So again, if some of the operations are sign extended, this signed, you have to work out the sign extension on a per register basis. Saturation, which is needed for audio, is you saturate at the post result, from the post result width down to the destination width. And this is one of the modes that we can add, and we also decided to add in that if RC equals 1, for condition registers, that the overflow bit is set if the saturation occurred. So that will occur on every single element. So you'll get an indicator of whether each element and which ones overflowed due to saturation, which in VSX you get a general indication there was an overflow somewhere in one of the results. was this thing? Yeah. Uh, okay. So just a quick recap. We've added with adding no actual vector instructions at all. We've added vsplat, vinsert, vreduced, 8-bit operations, 16, 32. We've added predication. If you're familiar with vector instruction sets, you'll notice that vcompress and expand are missing, as is map reduce capability, and vgather and scatter. So before we get onto that, we added in Subvl, subvector links, where the key feature of it is that the predication applies to the whole of the subvector. It does not apply to the individual elements of the subvector, because Subvl takes care of that in a different fashion, and this saves you on the number of bits in your masks thing, so you can treat your vec 2, 3, or 4 differently. Subvl, again, we're storing that as a 12-bit immediate and is applying it as a context, but there's so much data that we actually have to apply it separately. This is it's very common for vector instructions to be 64 or even 128-bit. So we've had to do some intelligent thinking here, creative thinking here. We have taken the opportunity to allow the Subvl to specify that the source or destination is a 0, 1, or a 0.0 or 1.0, because a huge number of operations in 3D things include inserting of those constants 0 or 1. Twin predication. I think probably the last thing I'll be able to cover in some depth. The twin predication, basically you have a predicate for source and for the destination, which has never been seen in any architecture before. And what it means is that you have two elements that progress on, and the simplest way to view it is that it is a multiple ordered vinsert. But the thing is that you can do vcompress and vexpand by this as well, because you do vcompress, you set the predication on the source, and vexpand, you set it on the destination. I think that's the right way around. But if you do both, then it turns out to be it puts vcompress and vexpand back to back, and you end up with an operation as I've never seen in any other vector instruction set, which is a multiple ordered vinsert. It's really quite. It's like, where did this come from? Thing. Now, the one thing that's missing is scalar operations. Typically, scalar instruction sets typically do not have this one where you look up the register in a register and then use the value of that register to look up which register you're going to look up. Right, but this is the basis of vgather and vscatter in vector instructions, and once you have that, we've called it move.x. Once you vectorize that, you end up with vgather and scatter, and you can't do it any other way. You can't do it with a twin predication, because twin predication is ordered. We added a hook system into. We also added in this predicate result system, which you hook into the predication system to analyze the result afterwards, and then if that post-analysis test was true, that's it. That's everything I would do. If the post-analysis test was false, then the result would not be stored. The condition register would be stored, but the actual result would be skipped or zeroed if you have zeroing. So we'll have to see how that goes, because that's quite an experimental thing that will be very, very interesting to see how that ends up being used. But the uses include floating point overflow, where you didn't want values to be destroyed if they overflowed. Many other uses would have to think about it. But you can also apply this to the condition registers themselves. The vectorized condition register operations can have this post-result analysis. So that's going to get really interesting. Apologies for running out of time. Fail on for data dependent fail on first. Basically, the vector length is truncated at the first page faulting byte load, and then the rest of the operations can occur, and you can do the store thing, and we're adding that feature to a thing. So yeah. There's a data-dependent version of that as well. The instruction thing. So basically, yeah, that's it. That's it in a nutshell. Is the basis is just you do not add the vector instructions. You add this context which vectorizes the scalar instructions themselves, and consequently, we can reach 90% power with good vector instruction sets with no instructions at all, except for Subvl. And if you start adding things like MoveX and a couple of others, you can reach 95% power with really good vector instruction sets with just adding like 3, 4, 5 instructions. It's cool. Consequently, researchers adding new instructions do not need to be concerned about adding a vector version of the exact same instruction. They add it to the scalar instruction set, and it's automatically vectorized. So, thank you very much.